Good afternoon. Good afternoon. It's my great pleasure to be here again for my course, Engineering Thermodynamics. As of now, I am in last module, that is heat transfer and compressions. I have already completed my 3 lectures on heat transfer. This is my 4th lecture, and I have covered the introduction to heat transfer, then conduction, then convection. In this, we have defined the heat transfer. We have also defined the conduction. We have also defined the convection. We have found out the coefficient of conductivity, that is K. Also, we have found out the coefficient of convection, that is H, by the Newton's cooling law. Also, from the Fourier's law, we have found out the conductivity. Now, I am in the 3rd mode of heat transfer, that is the radiation. And in broad term, we can say that it is thermal radiation. Before I start, as of now, we have already completed Module 1, Module 2, Module 3 and Module 4. In these modules, we have seen the 0th law of thermodynamics, 1st law of thermodynamics, 2nd law of thermodynamics, 3rd law of thermodynamics. We have also seen different power cycles, that is the absorption power, work absorption power cycle and work producing power cycle. For the work producing, we have seen Otto cycle, diesel cycle, dual cycle and the Brayton cycle. And for the power absorbing, we have seen the Bell-Coleman cycle, and we have studied, we have done number of numericals and we have derived so many equations on that. Today I am going to discuss about thermal radiation, and this is the one of the mode for heat transfer. In this, we have some topics. They are the introduction to thermodynamic radiation, Stephen Boltzmann constant, absorptivity, Kirchhoff's law, radiation, heat transfer. These topics I am going to discuss today. Before this lecture, I have completed the convection, introduction to convection, types of convection, Newton's law of cooling, convection heat transfer coefficient and numerical problem on this. So convection, it is mostly between solid and the liquid or liquid to solid. We follow the convection. So if you see here that this is the solid, it is solid slab, and here the water, the hot water is flowing here. This is the hot water. This hot water will give, this is the H, which is the convection heat transfer, and heat will transfer because this is the T infinity 1, and here is the air. This is the T infinity 2 and this is the T. So this T infinity 1 is greater than T1 and this is the greater than T infinity 2. So heat will flow from this side to this side. And if you talk about the types of convection, we have the different types like fluid to solid, solid to fluid. We have also phase changing, that ice to water, water to vapor, and so on. And we have also found by the Newton's law of cooling that this Q dot is equal to HAS T1 minus T2, where this H is the convective heat transfer coefficient. This we have already seen, and we have solved one numerical also about the heat transfer in a from house to the atmosphere. This we have already covered. Now, introduction to thermal radiation. So we have to understand first what is the thermal radiation. So thermal radiation or radiation is the energy emitted by matter in the form of electromagnetic wave. So in this, it will transform in the form of electromagnetic wave or photons as a result of the changes in electronic configuration of the atoms or molecules. As and when it is heat is transmitted as electromagnetic wave, it is called the radiation. Unlike conduction and the convection, the transfer of heat by radiation does not require the presence of an intervening medium. In this, we don't need any medium. But that is without medium, it will transfer the heat like it is coming from sun to the earth. In between, there is no medium. It is like a vacuum. Still, we are getting the heat. In fact, heat transfer by radiation is fastest at the speed of the light. So it is very fast. It is traveling at the speed of the light. It suffers no attenuation in a vacuum. So it doesn't differ if it is vacuum or without vacuum or atmosphere. It is not matters. This is how the energy of the sun reaches to the earth. So from the sun, the energy which is reaching to the earth by the means of the radiation. In heat transfer studies, we are interested in the thermal radiation. So we are interested about the thermal radiation, which is the form of radiation emitted by bodies because of their temperature. So if there is one body here, A, another body is B. So if this is a hot body, so it will emit the radiation. It will emit the radiation and it will reach to the another body. It is not concerned whether you have the medium or not. So, which is the form of radiation emitted by bodies because of their temperature. So here this temperature is important. T1 and this is the T2. T1 is greater than T2. It differs from the other form of electromagnetic radiation such as X-ray, gamma rays, microwaves, radio waves and television waves that are not related to the temperature. So this thermal radiation is very, very important, that here a hot zone should be there. A high temperature is required to radiate any body and to transfer energy from one source to the another. All bodies at a temperature above absolute zero emits thermal radiation. Any body which is in the earth or in anywhere, it will emit the radiation, and this radiation is directly proportional to the temperature, and it is, we will be discussing that it is into T to the power 4. So radiation is a volumetric phenomena, and all solids, liquids and gases emit, absorb or transmit radiation to varying degree. Every body, it is dependent upon how much size. It is called the volumetric phenomena, and all solids, liquids and gases emit, absorbs or transmits. It depends upon its temperature. If it is a high temperature, it will emit. If it is low temperature, it will absorb, and they will also transmit from high to low. Radiation to varying degree. If this degree is dependent upon the how much this thing is temperature is there. Radiation is usually considered to be a surface phenomena for solids that are opaque to thermal radiation, such as metal, wood and the rock. So it is a surface phenomena. So it is like sun rays. They are coming and hitting the rock. So rock, the surface will be very much hot. And after that, the conduction will take place, and then slowly it will go inside. Radiation emitted by the interior region of such materials can never reach the surface. So the radiation incident on such bodies is usually absorbed within a few microns from the surface. So all the radiation which is coming, it is the surface which is absorbing most of the radiation. And after that, it is not radiating, but it will transfer to the inside, like room. If the sunlight is falling on the rooftop, your rooftop will be very hot, but your room will not be that much hot, but it will surely more hotter than the required one, because slowly it is transmitted by the convection and the conduction, and in this way the radiation will mostly affect at the surface where it is hitting. The first hitting, that portion is the main that is affected by this system. Now we will see about Stephen Boltzmann. So the maximum rate of radiation that can be emitted from a surface at a thermodynamic temperature Ts in Kelvin or the Rankine is given by the Stephen Boltzmann's law. It is Stephen Boltzmann law. So the maximum rate of radiation that can be emitted from a surface at a thermodynamic temperature Ts in K or R is given by the Boltzmann constant. So this Q emitted maximum is equal to, this is the sigma As Ts to the power 4. Sigma As Ts to the power 4. So here sigma, the value of sigma is 5.670108 watt per meter square per K to the power 4. So this is the unit of this sigma, watt per meter square K to the power 4. So it is directly proportional to the Ts to the power 4, means the temperature of the body, and in this to the power 4, As is equal to surface area, and this sigma is the a constant which is called the Stephen Boltzmann constant. So the idealized surface that emit radiation at this maximum rate is called the black body. So if any object which can transmit or which can emit radiation at this rate is called the black body, and the radiation emitted by a black body is called the black body radiation. So any black body which is the body which can absorb any heat, and if it is transmitting in this ratio, in the proportionate to the sigma As Ts to the power 4 is called the black body, and the radiation is called the black body radiation. The radiation emitted by all real surfaces is less than the radiation emitted by a black body at the same temperature and is expressed. So this is the radiation emitted by the black body. And this black body is the maximum radiation is this much. But a real of how much? So here this you can see here, black body, here epsilon is equal to 1, Ts is equal to 400 K, and Q emitted is equal to sigma T to the power 4, 1452 watt per meter square it will be emitted. So here Q dot emit is equal to epsilon sigma As Ts to the power 4. So if this epsilon is the emissivity of the surface, so this emissivity, this epsilon is equal to 1 for black body. And other than black body, it will be always less than 1. Other than black body. So here the black body radiation, black body, the epsilon will be 1 if the temperature is 400, and so this emitted is equal to epsilon into T to the power 4. So it is 1452 watt per meter square. So if it is the black body, and this will per meter square it will emit 1452 watt. So this epsilon value will range from 0 0 to 1. So 1 for the black body and 0 for the fully. So this you can see here is a measure of how closely a surface approximates a black body, for which epsilon is equal to 1. The emissivity of some surfaces are given in the table. So this epsilon value is given for some material like aluminum foil 0.07, anodized aluminum 0.82, polished copper 0.03, polished gold 0.03, polished silver 0.02, polished stainless steel 0.17, black paint 0.98, white paint 0.9, white paper 0.92 to 0.97, asphalt pavement 0.85 to 0.93, red brick 0.93 to 0.96, human skin 0.95, wood 0.82 to 0.92, soil 0.93 to 0.96, water is equal to 0.96, vegetation is equal to 0.92 to 0.96. So this is the at atmospheric temperature emissivity of some materials are shown. So the if it is a less value, it means it is less emissive. If it is high value here 96 and all, it is for the water, it is most emissive property. So this is for the reference of this. So now next is absorptivity. Emissivity means it is emitting outside, but absorptivity means how much it is collecting, how much it can collect. Another important radiation property of a surface is its absorptivity alpha, which is the fraction of the radiation energy incidence on a surface that is absorbed by the surface. Like emissivity, its value is the range from 0 to 1. A black body absorbs the entire radiation incidence on it. So if it is a black body, everything it will absorb. That is, a black body is a perfect absorber where alpha is equal to 1. So this alpha is equal to 1 for the black body. Everything is absorbed. Every radiation is absorbed. That is, the black body is a perfect absorber. Alpha is equal to 1 as it is perfect emitter. So it is a emitter also. So alpha is equal to 1 and epsilon is equal to also 1 for the black body. In general, both epsilon and alpha or absorptivity of a surface depend on the temperature and the wavelength of the radiation. So the temperature T and the lambda, it is dependent upon these two properties. These things are represented. So next one law is there which is depicting about this absorptivity, emissivity and the absorptivity of the system, and that law is Kirchhoff's law. Kirchhoff has described this, how much it can be emitted and how much it can be absorbed. So Kirchhoff's law of radiation states that the emissivity epsilon and the absorptivity alpha of a surface at a given temperature and the wavelength are equal. So the radiation states, the Kirchhoff's law of radiation states that the emissivity epsilon and the absorptivity alpha of a surface at a given temperature and the wavelength are equal. Means alpha and epsilon will be equal at the given lambda and the temperature. In many practical applications, the surface temperature and the temperature of the source of the incidence radiation are of the same order of the magnitude, and the average absorptivity of a surface is taken to be equal to the average emissivity. So alpha and epsilon are taken mostly same. The rate at which a surface absorbs radiation is determined from the figure. So if you can see here in this figure, the radiation is coming in this way, Q incidence. So some will be absorbed here and some will be transmitted. So it is Q dot absorb is equal to alpha Q dot incidence, and it is Q reflected is equal to 1 minus alpha into Q incidence. So this is the formulation that Q will be divided into the two parts. One is the absorption and another is the reflected one. So here the rate at which surface absorbs is determined from figure. If you see, Q dot absorb here, this one, is equal to alpha into Q dot incidence, where Q dot incidence is the rate at which radiation is incident on the surface, and alpha is the absorptivity of the surface. For opaque or non-transparent surfaces, the portion of the incidence radiation not absorbed by the surface is reflected back. So if it is the non-transparent or opaque system, some part will be reflected back. So this reflected back, this part will be Q dot reflect is equal to 1 minus alpha. Alpha is absorbed, total is 1. So 1 minus alpha into Q incidence. So that is the total. The difference between the rates of radiation emitted by the surface and the radiation absorbed in the net radiation heat transfer. So the difference between the rates of radiation emitted by the surface and the radiation absorbed is the net radiation heat transfer. So difference rate of radiation emitted by the surface and the radiation absorbed. So emitted and absorbed is called the net radiation. If the rate of radiation absorbed is greater than the rate of radiation emission, the surface is said to be gaining energy by the radiation. So if the rate of radiation absorbed means the rate of radiation absorbed is greater than the rate of emitted, then it is gaining the energy. Gaining the energy. Otherwise, the surface is said to be losing the energy. If Q dot AB absorbed is less than Q dot epsilon, then it is losing the energy or getting colder, and this is getting hotter here. Since it depends on the properties of the surfaces, their orientation relative to each other, and the interaction of the medium between the surface with radiation. So it is also depend upon at what angle your transmission is, energy transfer is taking place. That is also matters, and it is depend upon the surface and other properties. Now we will see the rate of heat radiation. How we have, just like we have find out the heat radiation for the conduction, heat radiation for convection. Now we have to find out heat radiation for the rate of heat. Rate of heat for the radiation we have to find out. If you see this here diagram, the radiation heat transfer between a surface and the surface surrounding it. So this is a red color, this is the surface, and heat is incidence from here, and it is also coming from here. Some heat is going in this direction, some heat is going in this direction. So here Q dot radiation is equal to epsilon sigma As T to the power 4 minus T to the power 4 surrounding. So it is the surrounding here, and this is the system. So how much it is transferring, that we will be seeing here. When a surface of emissivity and the surface area As at a thermodynamic temperature Ts is completely enclosed by a much larger or black surface at thermodynamic temperature, T surrounding separated by a gas such as air that does not intervene with radiation, the net rate of radiation heat transfer between these two surfaces is given by. So this is the one surface here, and this is the two surface here, this is the surrounding. So rate of heat between two surfaces, that is Q dot radiation, is equal to epsilon sigma As Ts to the power 4 minus T surrounding to the power 4. So here it is a T surrounding, and here it is a Ts. This is the Ts. So Ts to the power 4 minus T surrounding to the power 4, and this is the area, and this is the your emissivity, and this is the your, so the emissivity and the surface area of the surrounding surface do not have any effect on the net radiation heat transfer. So this epsilon and this area is not having much difference on this. So only temperature is the main parameters by which the heat radiation is taking place. Radiation heat transfer. Radiation heat transfer to or from a surface surrounded by a gas such as air occurs parallel to conduction or convection if there is a bulk gas motion between the surface and the gas. So this radiation heat transfer to or from a surface surrounded by a gas such as air occurs parallel to conduction or convection if it is more gas is there between the surface of the gas. So it is always parallel to the conduction. Thus the total heat transfer is determined by adding the contribution of heat transfer mechanism. So we have to add all this radiation, conduction, convection, all the things. For simplicity and the convenience, this is often done by defining a combined heat transfer coefficient H, combined that includes the effect of both convection and the radiation. So we have to take H because in this conduction plus convection is added. So the total heat transfer rate to or from a surface by convection and the radiation is expressed as. So here Q total is equal to H combined AS Ts minus T infinity. So Ts is a surface temperature and T infinity is a fluid or liquid which is surrounded by this system. The combined heat transfer coefficient is essentially a convection heat transfer coefficient H modified to include the effect of the radiation. So this in H we have to include the radiation also. So it is modified H, not the total H. So I think we are now very much clear that radiation is very important, and we are going to take in the next class about the next topic, energy balance, derivation of the energy balance for heat transfer, boundary condition and types, Newton's law of cooling, relation between K and H. This I am going to discuss in my next class. Be tuned with my next class for heat transfer. The references of my lecture is P.K. Nog, Engineering Thermodynamics, Tata McGraw Hill's 4th edition. Eunice Senegal, Michael A. Bowles, Thermodynamics and Engineering Approach, Tata McGraw Hill's. Any questions you are welcome to ask. My email ID is yddwivedi@gmail.com. So thank you very much for the joining. Please do like and subscribe this video. Also see my other videos, very useful for your undergraduate thermodynamic topics. Thank you very much. Please log in for my next lecture. Okay? Thanks.
Like, share and subscribe. Hit the bell icon for more updates.